Thanks for the opportunity to speak to the group today. I do have some slides, and I've got a pile of junk to look at. So, as mentioned, this is going to be a discussion of the Nano-Vna. Anyone own one? Do you use it? Excellent, excellent, excellent. And I've had one for a while, and it was only about 2 weeks ago when I said, oh, I got to give this talk here. I started to really seriously get down and dirty and use it. So I'm very happy that I do. If you don't have one, this is what it looks like. About the size of one of your pocket phones. Small battery-powered vector network analyzer. Okay, getting the feed going for the folks in Zoom land. A vector network analyzer is a device, a radio frequency device. It's not for LANs, internet stuff. It's a radio frequency device for measuring radio frequency parameters. Spent some time talking about some of those. I know there's a wide variety. I know there's a lot of knowledge in this group and out in Zoom land, but I wanted to put a couple of things up on a screen here to remind you of some of the particulars about some of what's going on with that we're measuring. If I could have am I going to ask you for slides? All right, next slide, please. Okay, so there's a better picture of the Nano-Vna. 2 RF ports, they're SMA connectors, SMA connectors are standard on there. And one of the things that you'll find if you actually start using this is you can't have too many adapters. You just can't, the investment in adapters is absurd. All right, but they're really handy to have. And we'll go through some of the particulars. This is an H4 model, costs less than $100 on, I don't know where I got it. It might have been probably, most likely Amazon, right? Got a main power switch up here. There's a rocker switch up here. USB-C in the bottom. It's a rechargeable battery, and you can also connect this up to a desktop, laptop computer from the bottom end there. The display, 4-inch display, has a number of display modes. I'm going to go through some of these here. You can put a lot of stuff up here at the same time, enough to really confuse yourself, which is a sign of a good piece of technology in my book. So, next slide, please. There are a couple of measurements that you can make with this. I try to summarize this here for everyone's convenience. Couple of different things. I put it basically into 3 categories: gain, impedance, and return loss. Gain, we talk about the voltage output divided by the voltage input, or power out. There's voltage gain, power gain. I rarely speak in terms of attenuation. When I speak in terms of attenuation, I'm speaking of fractional gain. It's just a tick. It's just a tick. Forgive me if you're doing that. But in general, in the RF world, we talk about the gain in terms of decibels, right? Which is a logarithmic scale, which anyone who's feeling mathy is going to love that. I'm going to try to get out of the way of the screen. The second is impedance. Right, impedance, I say very, very briefly, is the AC equivalent of resistance. Impedance is the voltage imposed on an RF circuit divided by the current flowing through that circuit. And that's an interesting space because it immediately gets us into the world of complex numbers, which are a laugh a minute, let me tell you. So we'll spend some time with that. Return loss is the third parameter, and that you're very familiar with. In the amateur radio community, it's routinely considered of SWR, standing wave ratio, which is a measure of return loss. Return loss is how much power is not absorbed by the load that's been hit with the load. All right, so if that's just a way of going through there. Next, please. Like I said, you can't have too many adapters. I pulled out a box here. I have the pleasure of using a couple of laboratory network analyzers, right? Things the size of small refrigerators, so I'm not bringing them in here. But I've got an even bigger box of adapters. So what I always have, for every kind of a connector that I'm using, I'll have 3, these aren't even adapters, these are the standard terminations. So here's SMA male, BNC female, BNC male, or plug or socket, if you want to be modern. Type N, a plug, type N socket. And over here, these might look a little familiar. PL259, have a couple of adapters like that. In each of these categories, I have 3 terminators. And you can see it well on the type ends here. An open, no connection on the other end, it's wide open. A short, copper foil soldered over the top of it, maybe a good solid short, and 50 ohms. Right? So in this case, since I've got the laboratory equipment, I was able to put a couple of resistors on there and tune it up to get an excellent load on there. I'm a big DIYer, so I'll buy whatever I need to, but I'll make what I need to. These aren't even the adapters. These are just the standards. So if you're going to work with the Nano, typically comes with SMA connectors on it. I put a couple of SMA to BNC adapters on it. All right, so we can do this. So we have that. And I just saw the other night a great thing that some I don't know who it was who did this, put some bulk-mounted BNC connectors on a piece of PC board, soldered to a bottom plate, and he had a nice mechanically solid thing. You got to be careful. You know, you're carrying around one of these things in your coat pocket, and there's a chance, non-zero chance of breaking it. Nice to have something a little bit more mechanically robust, and I'm going to be building that next weekend because I don't have any more time this weekend. Next slide, please. Oh, there's the picture of it. This is beautiful. I love this. This is great. Just get a couple. And he did it with type Ns, because the type Ns, of course, are much heavier, and the cables that you're using, there's a lot more stress on these small SMA connectors. So pretty handy. Next, please. There are a lot of things on the web to help you with this device. A lot of, it's like everything else on the web, right? 95% of what's out there is garbage. But 5% is really, really good. And you just got to keep searching around for. This is a very nice third-party manual written by Gunther Kraus. And you can see a lot of good stuff with that. There are a lot of YouTube videos. Again, 9 out of 10 are pretty awful, but 1 out of 10 pretty good. So find your own. Your mileage may vary. Don't listen to me. I'm one of the 95% of crummy ones out on the web. Next slide, please. So again, I have these identified. These traditionally, in the RF world, I've always bought things from Pasternak, good solid RF supplier. Now you can get them from Kmart. It's pretty ridiculous, but you get what you pay for. Besides having the short, open, and load, also want a couple of adapters. Now we start talking adapters, and these are the same connectors type adapter. There's a SMA male to SMA male. Here's a SMA male to a SMA female. And there's a couple of those floating around in this box here too. It's a handy box to carry all that stuff in. Next slide, please. It's okay. You can see them. Okay, now you can just get a better look at them. I'm really trying to give you, if you haven't had the experience to see these, I think some of these visuals will help let this fix better in your mind. You'll note that these well-designed ones all have the same physical length. All right, as you know in your work with VHF and UHF, the higher frequency you go, the more important distances are. So getting them, the ones that are higher quality, they have the same physical, hence electrical length to them. Next, please. In order to make this thing work, it's got to be calibrated. This does not come out of the box calibrated, and it needs to be. It's capable of measuring a bunch of different things, and we use these terminations, short, open, and load, to accomplish that. The method that it uses it, and we're going to get this in front of a camera in a little bit here, but it's pretty small, and I'm going to be like juggling a microphone, and this. Maybe I'll try juggling. We'll get a couple of things, so you can see it better. There are several kinds of, like I said, several kinds of measurements. Recall that there are 2 ports on this. If you use it in a 1-port mode, you can measure the impedance of a device. You measure the impedance of an antenna, for example, or measure the impedance of a tuned circuit. This is I've brought a couple of pieces here. I'm kind of dug through my junk box. My basement is a little emptier now, but this is a box, and this is an example of something we use in the laboratory. This is not an NMR probe, but this is what's called an NQR probe. It's simply a tuned circuit. 2 high-power Teflon piston capacitors and a coil with some ceramic capacitors in there. The purpose of this is to connect to an NQR spectrometer and generate RF magnetic fields which can interact with materials, and we can answer questions like, how did we get here? I mean, that's what we do with that. This is a device, single port device, and we can use the Nano to tune this, and I'll show you how we can do that too in a little bit. We do that by measure reflection. If you have a 2-port device, like an amplifier, low noise amplifier, high noise amplifier, I guess we have a bunch of high noise amplifiers around, whatever kind of amplifier you have, 2 ports, an input and an output, and you can use the 2 connectors to study that device. There are a number of interesting parameters that you want to know about your amplifier. You want to know what its gain is. Hopefully it gives you gain and not reciprocal gain, which we call attenuation. You also want to know how well matched it is to 50 ohms, because you want it to accept and absorb all the power that's incident to it so that it works efficiently. Both of those can be measured with the Nano. Next slide, please. Yes, please do. And let me before you start, please interrupt me with questions. Heckle me at your own risk, but ask plenty of questions. Thank you.
Turn the microphone on.
And I'll repeat the question too. Is this thing turned on?
Can you hear me now? Oh, there we go.
There we go.
So when you use it in pass-through mode to test an amplifier, do you have to be careful you're not going to blow it up?
You bet you do. That's exactly right. Anytime you're working with any kind of power of any sort, you've got to be a little bit careful. In fact, this is a very low power device. It typically operates from 0 dBm, 1 milliwatt, to minus 15 dBm, so down to about 30 microwatts. So it's very safe for your delicate low noise amplifiers. But when working on this, if you're taking a look at a larger amplifier, a couple of watts or something, you can wipe it out pretty easily. Another question.
Okay. One of the things I just bought and have been playing with.
Congratulations.
Is yeah. I spent from my food budget a mini circuits limiter.
Yes.
It's 500 kilohertz to 3 gigahertz, and
Nice
limits to plus 13 dBm out.
Okay. Is it packaged with
Right
connectors?
here in my fingers. In fact, I'm inviting you to have a look so you can display its behavior on your screen.
Let's take a look.
Because of course it's not perfect. You can't.
You're not going to get this back, you know.
You owe me $65.
A bargain at this. Well, I'll pass it back for the moment, right? SMA male, SMA female, and it's a limiter. You say plus 13 dBm from a few hundred kilohertz to a few gig. That sounds like typical mini circuits hardware.
And
$65, nice deal. Why do you have this?
Because I have something that blows out at plus 15 dBm.
Why are you putting more than 15 in it?
Because I go up to places like Buckhorn where NPR has a transmitter.
Oh, okay. All right. There's usually a reason. Just want to get
the other thing is its limit is plus 33 dBm. So
okay.
it's
So
not
it can't take more than
indestructible.
about 2 watts.
About 2 watts, yes. But anyway, it's interesting to plot it because it's not quite linear at around 500 kilohertz, but it gets very, very smooth from 1 megahertz up.
Now, there's an interesting feature that we don't have on something as inexpensive as this, is we don't have amplitude sweep. There is some degree of amplitude sweep on here, but what you want is one of them to follow that device more more extensively is the ability to sweep the amplitude rather than the frequency, or both of them, and go for multidimensional analysis, which is even more fun than one dimension, where you actually look at the power and the frequency at the same time, or plot them up there in some very attractive graphs. We don't have
in
all
the
of that
case of
capability.
mini circuits, I kind of trust their data sheets. Not everybody
Me too.
can do that, but
I'm with you on that. Totally with you on that.
okay. Who gets the
All right,
mic?
thanks. And please, more questions. I'm happy to field questions. I think this has got to land. This is a visualization of return loss. All right, the concept of a source of radio frequency, power, energy, signals, delivers that energy to a transmission line, and it ends up at a load. The load either accepts it or reflects it back. It's one of the two things. Anything that it does not accept, it reflects back, which is not what we want, generally speaking. We want efficient transfer in the RF world. So return loss is a measure of that. We can measure the incident power and divide that into the reflected power, take the logarithm of that, multiply it by 10, and we'll get the return loss in decibels. We can do the same with voltage if we use 20 instead of 10. Salud. Next slide, please. Suiting the deed to the word, there it is. If you take the powers, take the ratio of the incident power divided by the reflected power, 10 times the logarithm, gives you the return loss. Or this is true for any decibel relationship. We'll do that in there. Keep in mind, we always report, when we report gains or return losses, they're decibels. You don't have to say whether it's voltage or power measurement, because they both are embedded in there. And you'll either measure it with voltage or you'll measure it with power, but you'll get the same ratio, the same value. Next, please. And as I mentioned, return loss. I keep forgetting. I had all these good slides here, and I keep talking about them before I have them up there. And this is the way we measure return loss. Okay, and there's often a sign convention that we have to keep track of that too. Next slide, please. Now, to measure impedance, I'm going to start talking about Smith charts. Anyone familiar with, how familiar are we with Smith charts? We don't have to answer that all there. So a varying range of familiarity with Smith charts. Smith charts are a remarkable graphical device developed in the 1930s, not the 2030s, the 1930s, by some Bell System folks, conveniently named Smith, that take impedance, complex impedance, resistance and reactance, and plot them in such a way that it brings out some of the underlying truths about this is some of the beauty of science there, when you actually figure out something and it reveals some deep truth about the universe. And the Smith chart does that. We can typically talk about using a Cartesian coordinate system, a rectilinear coordinate system. And we could have the real part of impedance and the imaginary part of impedance on two different graphs. And that's beautiful, that's wonderful where it is. But it doesn't show some of the beauty until you warp that around like this and turn it into a circular chart, where instead of these lines of constant resistance and constant reactance, we have circles and arcs of constant impedance and constant reactance. And then the magic starts to happen. When you start dealing with transmission lines, what looks like it really complicated over here, involving complex, and I mean mathematically complex, not complex hyperbolic functions, become simple circles here. So it's a wonderful thing. And if you're working with RF engineering, that's a big thing. Now, turns out this little baby does it for you, right? It knows it's been programmed enough. It's hard to see. Let's see. How does that look? Oh, down here? Great. Thank you. So, Smith chart, and there's a little bit of a yellow arc on here. That's because I've calibrated a bit on this, and we'll get back into more of it. Get the lights out of the way. That's good enough for now. Thank you. Thank you. We'll come back to that. Next, I'm just going to tease you with that a little bit. We'll talk a little bit more about that. Keep going. A bit more of a Smith chart, And again, a little bit of a tease here. There are special points on this space here. Dead center on this chart here is the characteristic impedance of the system. And for all of us, that's 50 ohms. If you're working in cable television, you're working with 75 ohms. I always wanted to know when I started learning about this, why 50 ohms? Why the heck is everything 50 ohms? And I found the answer to that in a 1960s Encyclopedia Britannica. You want to know? Okay, the reason is it's a compromise between two values. In coaxial cables, if you consider the power handling capability as a function of the diameter of a transmission line, the bigger the transmission line, the more power. That's a no-brainer. But if you take and look at the characteristic impedance, which is the ratio of the outer diameter of the outer electrode diameter to the inner diameter, the maximum power handling capability for any size cable is at 30 ohms characteristic impedance. So if you're working on radar stuff like these people were back in the 40s and the 50s, you want to handle a lot of power. Good. On the other hand, if you're carrying small signals, the same kind of consideration says what ratio or impedance gives us the lowest loss, 75 ohms. 50 was chosen, I think, at the flip of a coin as to be a compromise between the two, and we're stuck with 50 ohms. That's why you'll see cable stuff is 75 ohms, because they're not worried about carrying a lot of power, they're worried about loss. Anyway, so whatever you're using, whatever number you're using for your transmission line, that's dead center. That's one. So we'll call that 50 ohms for our purposes. Over here at the far right is infinite resistance. This is a line here of no reactance. Here, this is an open circuit. This is a short circuit. So when we use these standards and we calibrate our device, we adjust things so that our open circuit appears here. When I say we adjust it, we don't adjust anything. The computer inside here, a little microprocessor, figures out the particulars. We tell it, this is an open circuit. And he's like, okay, boss, there's no short circuit. Got it. And then it goes and does its calibration over the range of frequencies that we use, that we want. Next slide, please. Now, a lot of times when you start working with these network analyzers, you start hearing people talk about S parameters. And those are another handy way of describing these. I'm not going to go in too much detail because I just want you to at least, when someone says S parameter, you can nod your head and say, yeah, I heard about that. Don't worry about this. Let's get on to the important stuff. S parameters is a bit of matrix algebra that allows some clever kid engineers to cascade a bunch of devices one to the next and use some really simple matrix algebra to make them happen. But they look the same to the more jaundiced eye. They're the same thing. S11 is what we're calling return loss. Excuse me. On the input, S22 is the return loss on the output, and you might, if you're being clever, you might say, well, how do you get return loss on the output? The output is an emitter. It can have it. It can still have it. When it's not emitting, it can have a return loss. It's a mathematical definition. It has certain subtle practical details, but we're not going to worry about that too much. And the forward gain is given by S12, right here. And the reverse gain is S21. So those four give you the same kinds of parameters, and it can allow you to completely characterize a two-port device, something with an input and an output. This here is a one-port device. So I know it's got three things coming out here, but those are tuning wands. One port means one connector and one connection to the outside world. Next slide, please. Now, there is a relationship between SWR, or often called VSWR, the voltage standing wave ratio, and the return loss. common to use, the engineers use either a gamma or a rho for the return loss, and that's a number between 0 to 1. Right? We're not doing it, we're expressing it in decibels now, but we're just a number. The return loss is 0 to 1, right? You can't, you apply certain power to a device, and it's going to reflect it. If it figures out how to reflect more than you provided, I want a piece of that patent. All right, let's talk about that. We'll do that. So you can't. I'm not going to go through the second law of thermodynamics. It goes from 0 to 1. Goes from 0 to 1. And it's easy to convert that to Viswar. All right, Viswar goes from 1 to infinity. Next slide, please. I believe I have a table. So you can go both ways. All right, and it looks really fancy when you put Greek letters in a slide, so I think that's always a good thing to do. Next slide, please. 1 port and 2. I'm going to talk just to to say, so that it's just like my students in class. You can't say that I didn't tell you about this. You can't say we never saw it. You saw it. A 1 port device like this, single port, or a 2 port device like this filter, this K&L, this lovely K&L filter, two SMOC connectors, high power, 2 ports, 2 connectors. So there's a 1 port on this side, 2 ports on this side, and you can have them in 2 fashions, right? Balanced and unbalanced. The unbalanced, we typically use a coaxial connector, and there's a relationship. One is at a higher potential than the other versus balance, right? We look at twin line. That's a balanced kind of cable. And if you're doing a 2 port device, you've got 3 possibilities. They could both be balanced, both be unbalanced, or mixed. A balun. I know I'm preaching to the choir on this. Next slide, please. You can also take a look, and this is a great engineering textbook which shows resistive attenuators, and they're just a bunch of resistors, but you can look at unbalanced, balanced, unbalanced T's, unbalanced L's, unbalanced Pi's, and see the whole thing. So there's a whole topology that's worth learning about to some degree. Next slide, please. At this point, let's stop with the slides here because we've got some details here. Let's take a look at some of the things we can do with the VNA. So this is what's going to get interesting here as we try to do this. Oh wait, we'll get the little demo camera going, and we've got to do a couple of things. We've got to do some calibrations. And let me show you some of the particulars. What do you think?
I'm getting a lot of reflection.
We'll unscrew some bulbs. I'm not opposed to unscrewing light bulbs when necessary. In the quest of science. Okay, so what we need to do with this. Cool, very good, very good. So here's the display. Thank you for that. This is a display with a Smith chart. It's a touch screen on this, so we got it. We'll I'll see if I can do this upside down.
I can turn the camera. You get back to you. There you go.
All right. So we've touch screen, and if you have, my daughter says I have meat paws or sausage fingers. So if you got big fat fingers, you want to get a stylus. It comes with a what is basically a little guitar pick, and you can tap things like that. I also have a stylus in my little kit because I'm used to touch screens and fighting me with the size of my fingertips. So what we can do is we have a number of different controls on this. Let's take a look first at the display that we have on here. The display, we can run this as a Smith chart or as a standard 2-dimensional graph. This here. You're doing a great job. I just want to say you're holding it real steady. This is a graph which shows frequency on the horizontal axis, and in this case, return loss on the vertical axis, right? And nothing's connected to it. So everything's getting reflected. The yellow line is up at 0. I can go back in here and say, let's go over to the Smith chart. And now you can see we get a little more information. Everything was returning at 0, but as the frequency as the frequency moves, as we move through frequency, it shows some different behavior. And what we're seeing there is the change, the actual impedance of it. Now, what I can do is calibrate. Go ahead. I'm going to lean that on here. It's a tough job. Someone's got to do it, right? That's right. So let's go back here and let's go in and let's calibrate on these connectors, all right, which are just the short connectors. So I'll go calibrate, and it says, give me an open. Like, okay, I'll give you an open. Here, let's put this right under the screen. If you look at that, see, there's no center pin on this. So that becomes an open. We attach it right up here. Hit.
Why attach it open if the microphone?
The question. All right, now is the heckling starts. Two reasons. One is it provides a shield over the outside, and second, at higher frequencies, as you're well aware, at higher frequencies, the stray capacitance can actually become significant. So in practice, you don't absolutely have to use the open, all right? But I'm trying to be a good guy here and do what they follow. I read the manual. So thank you for that helpful question, sincerely. All right, so I hit the tab, and you look, there's a little blue line going across the top of it. It measured the values across the frequency range, all right? So now I'll pull this vestigial open, and here's the short. You see that there's a pin in the center of that. So this truly is coming up with a good dead short there. Put that on. Notice the display changes. Tap the short. The blue line goes across. It measures it. All right, good. It's happy. Let's keep going. One more. Third one here. We put the 50 ohm load. Everyone's got a 50 ohm load laying around. Notice that the data goes right to the center because that's a special place in the world of radio frequencies. There we go, got the line on there. All right, so now that I'm done, I can tell it I am done. I'm only doing the one port calibration here. See, there's a through there, which we're not doing. So I'll put that in there, and if I want, I can save it. It's got some registers. Notice now, the 50 ohm load is dead center. This is where it's supposed to be, all right? If I take that off and put the short circuit, did I mention that it's always important to use a certain amount of profanity when working with these connectors? Yes?
Is it good practice to do your stimulus before you recalibrate?
Before when?
Before calibration.
The stimulus. Well, okay, the question is, yes, I can. I will. Is it important to set stimulus before doing the calibration? And the answer is, it depends. I hate that answer. Okay, generally speaking, you get into a groove where you've got your machine set up and you're working with passive devices, and the manual, the Nano manual says minus 15 dBm is a great place to be. It says that's good. It works at minus 10, minus 5, and 0, which you can get to. So in many cases, not a big problem. There could be circumstances, especially if you're dealing with some of these nonlinear devices and some ACT devices, you may want to be a little bit more careful with that. So I think that most of the time, like in many things, we can use the default values, but we always they always come back and bite us in the ass when we don't pay attention to the default. What's going on there? So there we go. All right. Notice now the short circuit is over. That's okay. That's all right. We got to figure out how to do this with a tripod or something. On the short circuit is at the. I told you it was at the far left. You think I was lying? All right. It's right there, and it's holding right there. It's right, just where it's supposed to be. Now I'm going to pull the connector, and I'm going to, with no connector on there. You can look at the far right, and thank heavens this is a little bit out of focus. It's hard to see. There's a little bit of a line here. This spot here was a dot. We're operating here from 10 megahertz up to 600 megahertz. I just put 10 to 600 because that'd be a good place to be fooling around with. There's the tiniest effect of not having the connector on there, and it's going to be hard to see. It's going to be hard to discern, but that I can see over here, it is more of a dot with the cap on it. So it's a good thing to have. Okay, cool. That's great. So I'm going to take this and I'm going to climb up a tower and I'm going to hook this up to my antenna. And I'll be basically trying to juggle this while not falling off the antenna or the tower. Not very helpful. We usually measure things at a distance. But let me do this right here and now. I'll pull out a BNC male-to-male adapter. Attach that there. I made a little monopole. And it's not a random length. I actually chose it, but it's arbitrary. All right? It's not a cut for any particular frequency that we would be finding interest here, but I just made it. And I thought this would be a fun thing to do. Let's see if we can tune this baby here. So we're going to have to hold this up right here. So we look at this here on the Smith chart, and what we're seeing now is the impedance of this antenna as a function of frequency. At one frequency, it's close to the center there. It crosses the vertical, what is the horizontal line here. It crosses that, so that's where it's resonant, and it's getting close to the center. So it has some being close to 50 ohms. There's the point where it's resonating, and this is now 356, 352, 344. You see, it's all over the place, right? Because I'm in its near field. I'm all over this antenna like a cheap suit. All right? If I touch this here, it detunes it. I'm all over it. This is not a good measurement. I'm too close to it. What I really want to do is I want to be far away from it in this case. But we'll fix that in a few minutes. You're doing fine. You're doing fine. Just get rid of the reflection, see the display, all at the same time. We'll come back to this. All right, we'll see if we can make that a little bit better. Oops. Let's not do that. But we can use this. This tune device here is shielded. I made it as a box. So it's got a shield. I got variable capacitors that are exposed here. We ought to be able to do something with this. Let's see how well it works.
Upside down. That's okay.
All right, right side up.
It's upside down, but that's okay.
All right, I am going to write it. I'm going to right side.
Right way for you.
Turn it. All right, I'm going to go this way. Okay, so now once again, we've got all these spirals. So we're seeing this is the remarkable stuff that goes on in our RF circuits when we're not looking. There's a lot of things going on. What I'm going to do here is I'm going to switch this right now to return a different display. We're going to display format log mag. So we're looking at the reflection loss, the return loss, and there's a dip over here. These are 10 decibels per division here. This line up here is 0, which is perfectly reflecting. And you can see over here at this frequency, there's a dip. That means it's absorbing there. It's tuned, give or take, to that frequency. What we can do is with this here, I can adjust the tuning by rotating these piston capacitors. So I rotate this one here, and we're changing the frequency. And it's also, you see the dip is shallower, so it's not as good as a match. What you need is the dip has to be at the frequency you're interested in, and it's got to be low. Typically, we say, I suspect that just about everyone here has an intuitive feel about what VSWR is a good value, where you'd like to be with your antenna. With return loss, 10 dB is you got to be at least 10 dB. You can get to 20, that's great. If you get 30 or 40, you're kidding yourself. Right? It's not going to stay that way. Things aren't that stable. So what I can do here is adjust these two values, two pistons. Let's see what we can do. See some effects. So I'm adjusting this other one, and I'm at the stop here, and it got deeper. If I want to bring this up, Let's see if we can, I'll adjust, there's a marker here, so I can look at the marker and it gives us information. Come on. There, so the marker is at 238 megahertz and it's minus 11 dB. So that's a pretty good match. That's, as we often say, good enough for government work. So we can measure that, and I can do that here. But problem is, if I want to do that antenna, I want to do these antennas. I brought some other antennas to show you. I have a dipole here. A dipole on a BNC connector. There's no way I can tune this if I'm sitting so close to this dang thing, right? Got another one over here. I thought we would take a look at some of these. Here's a dipole with, instead of being fine wires, has brass tubes. So we expect this to be a wider bandwidth. We'll take a look at that too. But the problem is we can't tune these when we're so close. So what we have to do is we have to put a cable in between the VNA and the device under test, and we have to calibrate out the cable. I'll show you how we do that. Certain amount of profanity.
Does that have to be Chinese profanity?
Anyone you like. Whichever one works for you. So here we have a cable. Piece of cable, nothing up my sleeve. All right, about a meter and a half long. Put this attach here. There we go. I'm going to put that up there. It'll be less of a drag on it. Let's change the display back to the Smith chart. Look what's happening. As a function of frequency, it's changing the electrical length of this physical piece of cable depends on frequency, and it shows up like a spiral on the Smith chart. Right? We're going to take that out mathematically in a moment. So let's find see what I did with here we have a BNC female to female, and see where I lost the standards. Here we are. Okay, here we go. Why don't you pull back a little so we can show a little bit more here. I'm going to the other end of this as the BNC, and I'm going to put an adapter in here, which is going to be just very small, and we're going to calibrate. Calibrate. Okay, I'm going to start with the open, just for you, Darren.
Okay, appreciate that.
All right, open. Open.
Sure you got that? It's open. Okay. Wide open.
Next, the dead short. And the load. When I'm done, I will instruct it to execute its little calculations. We'll save that in number 1. Come on. I hate software. I live my life on software. I'm gonna have to do it again. It didn't take. I had a systems engineer who worked for me a number of years ago, and she said, "Man, you're a real hardware guy, aren't you?" I'm like, yeah. I don't do the software. Software for me is like cats. I love them. Oh, all kinds of stuff. I had one here, and like everything else, I can't. Is this mine or yours?
That's mine.
Are you sure? This looks a lot like mine. Done. Save. Oh, come on. Calibrate. It shouldn't be. It's all closed. I've never seen it happen like that. Right. You're right. It should. I hate when people says it shouldn't. Is that the right value? It should be. Well, I know it should be, but is it? Yeah.
What was the question? What was your
Is
question? Oh.
It always works when you're doing it live, doesn't it?
Oh, every time. It's the art of not wetting your pants when you're doing a demo. I can tell you. All right, so I got all three of those there.
Oh, that would be.
A bad oh my God, that's never happened before. Nah.
Does it have the Hewlett Packard green button?
Ooh.
Reset.
Let's try it. We're gonna one more time before we give up. Input. That's good. Open. Measure that, baby. Short. And load. It's definitely not. It's not calibrated. Cycle the power. The next step. All right. It's actually cycling the power has worked far many times than I would hope for. We're going 10 to 600 meg. Good. Open. Now we're affecting the screen, all right? Good. Okay. Load. 16th time is the charm. All right, so there we are. Dead center. Here's the test. Lovely. It's sitting over there at open. All right, so we've calibrated out the cable. Now, once in a while, if I could have a volunteer from the audience, please. You. Someone close by. Just hold this up in the air. All right, so there we are. Now we're looking at the behavior of that, and hopefully it's Mark. Yes. All right, hopefully Mark's not detuning it too much. Let's go over and all right, it's resonating at about 360 megahertz. I'm going to go over and use the different display, the log magnitude, and you can see it's not too deep of a trough there, and it's a little low. If we want to do this for 420 megahertz, let's not blame Mark for detuning it. We'll just shorten it a bit. Look what happened. It went up in frequency. Who didn't see that coming? All right, so let's go over here. 400, so let's just set this for 420. What's someone's favorite 70 centimeter frequency? 432. Good enough for government work. All right. So there we go. I'm going to go a little shorter. Cut it longer. Now, but it's not deep. It's not deep. It's not 50 ohms. Thank you, Mark. You've been very helpful here. What do we need to do to this? To this monopole? We need to put the radials down around 40 degrees. Check that out. Oh. It really works. This thing really does work. I said this thing really does work. All right. Lets you tune antennas. Lets you tune things. You can see them. Edward Deming did not say what you can't manage what you can't measure. That's a misquote, but it's true. If you can't measure it, it's really hard to get it designed exactly what you want. Okay? So you can do that. Let's take a look at something else. This is a souvenir for anyone who wants this. Here's a 70 centimeter J-pole. I'm sorry, I keep forgetting this. 70 centimeter J-pole. Let's see what it looks like. In a PVC case. Well, this has not been tuned. Let me show you what this looks like. This is a J-pole that I envisioned in a dream using coaxial cable rather than twin lead. I promised Ann I'd write an article of this for the newsletter on this, but I got to cut these lines a little bit to get this to tune better rather than hold it. That's another antenna. Yes.
When it deepened it, what were we getting?
We're getting a. Yes, I will. Thank you. The question is, what do we get when that dip gets deeper? That's a better match. It's two things. The return loss is getting lower. The load is absorbing more of the power. It's a better match. So it's been tuned. The position of we roughly say the position of the dip is the measure of the tuning. The depth of the dip is the measure of the matching. So better. Okay. Another question. He doesn't trust me. He's got to get the microphone.
Okay, the mic's not working. So
Okay, I'll repeat the question.
all right. I was just going to make a comment that the deeper the dip, the higher the Q.
Okay, the statement was the deeper the dip, the higher the Q, and that's not exactly right. I'm gonna dispute that. The width of the dip is more related to the Q. That's what we get. The width of the dip in relation to the center frequency is in fact the measure of Q. The wider it is, the lower Q, more broadbandedness. That's what I hope to expose that with this wobbly dipole. We'll get to that in a minute. More questions. All right, let's see. How are we doing on time? I'm seeing more people nodding off, so we're going to have to. Yes, a question.
I've got an antenna that I acquired years ago. I don't know what it's for. It's about this long. It's a tube about that big around. Inside the tube about that big around and about that long with a SO239 at the end. Commercial made, no markings, no nothing. How do I take my Nano?
Did you bring it with you?
No.
Okay, so all right, the question is.
How do I tell what frequency that thing is resonant?
Right. Okay, so the question is, an antenna fell off the back of the truck, and he got a hold of it, and wants to know what it's tuned for, right? Can't tell from that. This is exactly what we're doing right here and now. You get your Nano, you tune a cable, and you attach it to there, and sweep through the frequency range, and you'll find a dip. the depth of that dip will tell you how good of a match it is, but it'll tell you what frequency it's cut for.
So where at on the Nano does it do that? What setting?
So here's the antenna. That dip occurs at a certain frequency. The frequency scale is on the bottom. Oh, this is log magnitude. Yeah, let me display that. Okay. So we're okay. I'll describe it. So we're looking at the trace here is S11. This is on the upper left. Oh, you can't really read the top. This S11. It's return loss, and we're on the format is log mag. I personally like this one here because I can read the frequency off the bottom of the scale and see where that occurs.
Okay, but you have to start with these things. You have to start somewhere.
Right.
You can start at the bottom. Every time you turn this thing off and turn it back on, it always goes back to 50 megs and goes up to 900.
So, okay, it will until you save your current settings.
But we don't know what we're doing.
Yeah, me either.
We don't know if it's a 3 megahertz antenna or a.
Yeah, we don't. So, I mean,
Where do we start?
I voted with my feet. I started at 10 and went to 600. That's a pretty big antenna, is what you're describing. So I think if I was that one, I'd start at 1 and go up to 100. And I'd look. And if it didn't find a dip, I would go. I'd widen the search range. I'd go down to 0.1 and up to a couple of hundred.
And use log mag.
Yes, I would. Not everyone would agree. I mean, there is some standards of operation, and then there's some personal style. You looking to say
And then
something?
you're getting rid. What trace are you using? Just
Uh,
the
So, all right, on this one here, trace 0. I just yeah. Too many traces on the screen, and I kind of lock up. That's my software problem. So I just use the 0 trace. Whoever I've got your. Okay. Yeah, give me that limiter too. Is that making sense? Is that making sense? Is this making some sense? Good. Okay. So let's take a look at some other ones here. Let's take a look at this dipole. See what happens. I'm going to set this down to remind me to pick it up again. So here's a dipole. You know, looks like about 3/4 of a meter long. Let's see if I can adjust this. It's about where's James? It's about 220. We should put this up on the mountain.
Antennas we don't need.
We always need antennas. So you can see it's this is very sensitive to my presence, and it's not because I have a special aura. It's because I'm a bag of salty water, right? Just like the rest of us. So it makes a big difference. Now, let's take a look at this in comparison with the larger diameter wire dipole and see what happens. They're about the same length. No accident there. Let's see if we can see the difference visually. Hard to see here, so let's zoom in on it. All right, I'm going to set this down. And I'm going to change, let's see, so I'm going to change the frequency range. Stimulus. Let's start at 150 megahertz, and we'll stop at 250 megahertz. Okay, so let's take a look at this now. The BNC center post has a lot of flexibility. So there we go, and we're running, so let's see, 1, 2, 3, 4, 5. We've got about 6 divisions, 100 megahertz from one end to end. It's about 15 megahertz per division. And if I hold this, if I stop jittering with it, you know, it's around 5 megahertz wide. All right, it's the dip. I'll set this down and let's try the thin wire dipole. Single band antenna. The antenna is for sale at the end of the program. Carpenters. Again, it's hard to see. What I really would need to do is I'm gonna have to get a tripod. I'm gonna have to get a wooden tripod and just set this up on a tripod so we can see that. Not a convincing demonstration of the difference in the tuning. So we'll just put this aside and forget about this for the moment. All right, we're running out of time here. Let's take a quick look at the slides and close this party down. Huh? Thank you for that there. Okay, so what we can do here, we can measure and we can understand a lot about what's going on with our antennas and our other components. I'm going to return this to you before I accidentally. Oh, I know what you're talking about. Thank you. Thank you very much. Thank you very much. So, you know, inductors induct, right? Capacitors capacitate, right? But they don't always do all that. Anyone who's spent any time at higher frequencies knows that sometimes it's not exactly what you put in the circuit, it's where you put it in the circuit, right? Because strays are incredibly important. Inductors are better modeled at high frequencies by an inductor with a series resistance and a parallel capacitance. And that gives us, would give us, if we were looking at it on one of these little VNAs, a plot which shows the phase angle and the magnitude. If you take the reactance and the resistance and convert them into polar coordinates, you end up with a phase angle and a magnitude, and that's what we can see. Capacitors, same thing. In some cases, we can actually model that as a parallel resistance, which is my preferred. Next slide, please. And capacitors similarly have their own behavior. Capacitor, some series resistance, and some series inductance. A nice capacitor and a capacitor with a large equivalent series resistance. That's not a very good capacitor. Next one, please. We can look at these. We can understand the way these parts behave. Let's go to the next slide. Doop. And resistors. Resistors don't also always look like resistors. Here's a high value resistor and a low value resistor. At high frequencies, the resistance falls off, and we have stray capacitance in there. Low values, we have series inductance. But we can visualize this and we can measure this with a VNA. This is the beauty of a VNA, is it reveals these details. Next slide, please. We'll get through this. Okay, so here's a table I put together. I think I have a graph on the next one there. What's the relationship between return loss and VSWR? Okay, nice VSWR, right? 1.006, it's really good. That's a 50 dB return loss. 1.02 is 40. So it's sort of like, the example I often use is if I said that the price of gasoline in Mexico City was 15 pesos per liter, would you think that was good or bad? Right? You need to get it converted into something you're familiar with on an ongoing basis to do that. So it's always good to learn a foreign language. So I've always used return loss. I try to use VSWR so I can talk Turkey with folks from other disciplines. Next slide, please. Okay, this is all about how we actually define complex impedance, but I think we should bring this to an untimely close. because I think that they're dropping like flies. Thanks very much for paying attention as far as you did. I hope you have fun with your Nano. I'm having fun with mine. More questions?
You said that was an H4?
Yes, yeah.
There's multiple models.
I know.
Do you have any comment on any of those?
It's a shit show out there. It's the one I bought. I probably bought it a year ago. It looks like it's a pretty good one. It's well reviewed. I have read some stuff that says there are size matters. It is a 4-inch display, which is a good one. That's nice. The earlier version was a 3-inch, and I mean I hate my phone, right? At least I have a tablet with a sizable screen. I need a big screen. It seems to have good performance and it works well. Another question, yes. Yes. It's very important. It makes a difference. It makes a difference yes. The question is, if you got an antenna installed at the top of a tower, it's not too easy to do the calibration. My answer is tough stuff. It's really a good idea to do that. If you get good with one of these things, you can start to anticipate the behaviors. But in the early stages, I say it's really good to get, sort of like driving a car, get a feel for the way the brakes work, get the steering down, and then you can go do it stone drunk. That's right. That's the wire. That's exactly right. That's exactly right. Now, if you get the thing tuned, that'll approach the center of the Smith chart. If you go into the log mag, you won't be distracted by those circles. The log mag is still an excellent display for tuning antennas, for tuning and matching antennas.
So a lot of us have multi-band, say 10 to 80. Would it be good just to, like you're saying,
Zoom in. That's right. The thing to recommend is to set the start and the stop in tight. You can do that, or you can just get someone to go up there, climb up there, and put the loads up there while you calibrate it. All right, then you do it while she's down there operating the rig. Works both ways. It's a very symmetric problem. Any other questions? Okay, thanks again for paying attention and not throwing too many raw vegetables.
This presentation was brought to you by the Northern Colorado Amateur Radio Club. For more information, visit our website, ncarc.net. Thanks for watching, and don't forget to like and subscribe.